Equations for motion with constant acceleration. In Unit 3 on velocity and acceleration, we will be using a set of equations, and the more familiar you are with these equations, if these equations are memorized, the faster you'll be able to solve problems, and the easier the problem solving will become for you. I recommend that you use a form of the equations that looks slightly different than what is used in your textbook, but the equations are essentially the same. One form of the equations involves objects that begin at rest, whereas there is a separate form of the equation whenever an object has some initial velocity to begin with. So let's take a look at these basic equations. We'll create a table. And on the left side of our table, we'll list formulas for objects that are already moving when they begin to accelerate. On the right-hand side, we'll have a special form of the equation for objects that begin at rest. And these formulas can also be used for objects that come to a rest. We'll talk more about that later. The first equation is for finding the final speed of an object after it undergoes some acceleration. This equation says that final velocity, or VF, is equal to the object's starting speed, which is initial velocity, VI, plus acceleration times time. Now in the book, sometimes they include a delta symbol in front of a variable to mean change. For example, another form of this equation might say final velocity equals initial velocity plus acceleration times change in time, where a triangle or delta symbol would be included before the symbol t. In most problems, however, it's understood that time is the thing that is changing. So by understanding change in time, if we eliminate the delta symbol, then our equations look much simpler and are much more manageable. If I have an object that's at rest to begin with, meaning that it's not moving at all and has no speed prior to its acceleration, then VI would equal 0 in this equation, and it would drop out of the equation altogether, giving us the simpler version: final velocity equals acceleration times time, or acceleration times change in time. So on the right-hand side, we have a simpler form of the equation on the left-hand side. So while in the beginning it may look as if we have lots of different equations to learn, really there are not so many after all. The second equation involves distance that an object travels during an interval of time as it's undergoing constant acceleration. So the second formula, if the object has some initial velocity to begin with, says that distance, or change in distance, is equal to the initial speed of the object, VI, times time, plus 1/2 AT squared. If the object is at rest in the beginning, then its initial speed would equal 0, and any number multiplied by 0 is 0. So VI times t is eliminated from the formula altogether. It drops out. So for objects that start at rest, the simpler form of the equation says distance is only equal to 1/2 AT squared. So it's really the same formula, only if the object starts at rest, its initial speed is 0, so the equation seems shorter. Now in the book, I would like to point out that the book uses different symbols to represent the same equation. For example, the book would say that distance means change in position in a particular direction. If the object's moving horizontally, your book would call the distance delta x, or change in displacement in the x direction. And then it would use similar equation, vi times t plus 1/2 acceleration times change in time squared. And so you'll notice that this equation looks a little bit more complicated, but essentially we're using the same equation. I prefer to use the symbol d for distance because it reminds me that we're talking about distance as opposed to calling it delta x. And if the motion were in the y direction, your book would use the symbol delta y. But distance is distance, and as long as you understand that the change in the distance is taking place either in the vertical direction or the horizontal direction, then you should feel comfortable using the equations that I presented you. Therefore, I will erase this more complicated looking formula from our table. A third equation can be used to find final velocity whenever the time is not known. This equation tells us that final velocity is equal to the square root, let me rewrite that, Vf is equal to the square root of Vi squared plus 2 times acceleration times distance, or Vi squared plus 2AD, all under the square root sign. So notice that we don't know the amount of time here for the acceleration, but we do know the distance the object has traveled and the rate of acceleration. And so using this formula, we can find final velocity. If the object is at rest to begin with, then the equation is simplified, and it simply says Vf is equal to the square root of 2AD. Now, one other formula that you might find rather useful in certain homework problems tells us that distance is also equal to 1/2 final velocity plus the initial velocity times time. This formula is useful if acceleration is not known, but if we do know the final speed and the initial speed of the object and the time that it's being accelerated. If initial velocity were 0, then the equation is even simpler, and it says distance is equal to 1/2 final velocity times time. These last two equations are not used as often as the equations above them, but they're nice to have in the event that acceleration is not known. However, we would know that it's constant acceleration. You should attempt to memorize these formulas. You should take them out, have them open on your desk as you're working your homework problems to look at, because it makes it easier to see when you know what's given in a problem which equation is suitable for finding the unknown that you're looking for.